Find the first three terms in the expansion of 1 minus 2x to the power of 5. Okay, so we're not going to expand the entire expression since we only require the first three terms. So the first three terms will be 5 choose 0 times 1 to the 5 plus 5 choose 1 times 1 to the 4 times minus 2x plus 5 choose 2 1 to the power of 3 times minus 2x squared. Okay, we could continue expanding this out, but we're not going to. We just require the first three terms. So 5 choose 1 times 1 to the 5, the first term, will just be 1. Then we can have 5 choose 1, which will be 5 times minus 2x, so the second term will be minus 10x. And then 5 choose 2 is 5 times 4 over 2 times 1 times minus 2x all squared will be 4x squared, so that's going to be 20 divided by 2 is 10, give us 40x squared. Given that the coefficient of x squared in the expansion of this expression is 12, find the value of the constant a. Okay, we've already established the first three terms for the expansion 1 minus 2x to the power of 5. So we are just going to concentrate on those three terms since all we require is the coefficient of x squared. That's why we were only required to find the first three terms of that expansion of that binomial, was because any other term thereafter was not going to yield a coefficient of x squared when multiplied by this polynomial. So the first three terms of that expansion were 1 minus 10x plus 40x squared. And now we're only interested in the coefficient of x squared. So we're only going to consider terms that will give a term in x squared. 1 times 1 will not do that. 1 times minus 10x will not do that. 1 times 40x squared will give us 40x squared. Ax times 1 we're not interested in. Ax times minus 10x gives us minus 10ax squared. Ax times 40x squared gives us a term in x cubed. We're not interested in that. 2x squared times 1 will give us 2x squared, and then we're going to get a term in x cubed and a term in x to the 4, which we're not interested in. So the coefficient of x squared in this expression is 40 minus 10a plus 2, which simplifying is 42 minus 10a. This expression, 42 minus 10a, is the coefficient of x squared, which we are told is 12. So we just equate that to 12 and solve for a. So 30 equals 10a, a equals 3. The point is moving along the curve y equals 2x plus 5 over x in such a way that the x-coordinate is increasing at a constant rate of 0.02 units per second. We're required to find the rate of change of the y-coordinate when x equals 1. Okay, so we have a curve, y equals 2x plus 5 over x. We are told that the x-coordinate is increasing at a constant rate of 0.02 units per second. Now, whenever you see the word rate, rate implies per unit time, and increasing implies change, right? Increase or decrease implies change. Now, in calculus, change is indicated by the letter D. The x-coordinate is increasing, right? It's still changing, so we are dealing with dx, and at a constant rate is per unit time. So we are being told that dx dt equals 0.02. We're required to find the rate of change. So again, change is indicated with d, the change of the y-coordinate. So looking for dy, the rate of change of the y-coordinate. So we are looking for dy dt. That's what we're required to find when x equals 1. We now have two differentials, dx dt and dy dt, and we need to now relate this to the curve that's been given to us. So from this curve we can find another differential. This differential will be dy dx, And then we're then going to relate these three differentials to each other. So let's just first find an expression dy dx in terms of dx dt and dy dt. The fact that we're looking for dy dt and we are given an expression dy dx, we have to relate the two via this differential dx dt. So if we look at the left hand side, we have dy dx, dy in the numerator, dx in the denominator. On the right hand side, we have dy in the numerator and we have dt in the denominator. So we need to eliminate this dt. And to do that, we will have to multiply dy dt by dt dx. What that does, it eliminates dt, and at the same time we have dy in the numerator and dx in the denominator. So we have dy dx equals essentially dy dx. It's just expressed in terms of two different differentials. So that's what we're going to do now. We're going to find an expression for dy dx. Before we do that, we need to get the curve expressed in differentiable ready form. So y equals 2x plus 5x to the minus 1. We can now find dy dx, which is 2 minus 5x to the minus 2, which is 2 minus 5 over x squared. So we have 2 minus 5 over x squared on the left. Dy dt is what we are looking for. And dt dx, we were given an expression dx dt. Dt dx is just the reciprocal of that. So we're going to multiply by 1 over 0.02. And this is evaluated when x equals 1. We need to find dy dt when x equals 1. So when x equals 1, we will have 2 minus 5 over 1, which is minus 3, equals dy dt times 1 over 0.02. So eliminating this denominator now, we just multiplying both sides by 0.02. 0.02 times minus 3 would be minus 0.06. The fact that this is negative just means that the y coordinate is decreasing over time. The curve is such that dy dx equals 12 over 2x plus 1 all squared. The point 1, 1 lies on the curve. We're required to find the coordinates of the point at which the curve intersects the x-axis. Okay, so we are given a differential dy dx, which is the gradient function or derivative function of a curve y equals. So since we are required to find the coordinates at which the curve intersects the x-axis, we will obviously need to know and find the equation of the defining curve. So given the gradient function, the derivative function, we will therefore need to integrate this expression to find the equation of the curve. So y will equal the integral of, and we'll take this 12 out as a constant, 1 over 2x plus 1 all squared dx, which equals 12 times the integral of 2x plus 1 to the minus 2 dx, 12 times, when we integrate the 2x plus 1 to the minus 2, we're adding 1 to the exponent. So 2x plus 1 to the minus 1. We then divide by minus 1. So we just put the minus in front, just so it's neater. And we also multiply by 1 over the derivative of 2x plus 1, which is 2. And then also we add the integration constant to c. So y equals 12 divided by negative 2 will be minus 6 times 2x plus 1 to minus 1 plus c. We just write that as minus 6 over 2x plus 1 plus c. Now to find c, we use the fact that the point 1, 1 lies on the curve. So we're going to substitute the point 1, 1 in. 1 equals minus 6 over 2 plus 1 is 3 plus c. 1 equals minus 2 plus c, so c equals 3. The defining equation of the curve is therefore y equals minus 6 over 2x plus 1 plus 3. Now that is the curve. We now need to find the coordinates of the point at which this curve cuts the x-axis. So in other words, we want to know what the x-intercept is. So we put y equal to 0. 0 equals minus 6 over 2x plus 1 plus 3. So 0 equals minus 6 plus 3 times 2x plus 1. 6 equals 6x plus 3. 6x equals 3. X equals a half. So the curve will cut the x-axis at the point half 0. Question 4. Prove the identity sine theta plus cos theta times 1 minus sine theta cos theta equals sine cube theta plus cos cube theta. Now, there are a couple of ways we can go about doing this. We can either start with the left-hand side, multiply out these terms, and use the square identity to simplify. Alternatively, if we start with the right-hand side, we can factorize using the sum of two cubes. That actually might be far easier. So for once, we're going to start with the right-hand side. Which will factorize as the sum of two cubes. So we'll have in the first bracket sine theta plus cos theta, and in the second bracket we'll have sine squared theta minus sine theta cos theta plus cos squared theta. So we have sine theta plus cos theta. Sine squared theta plus cos squared theta equals 1 from the square identity. So we have 1 minus sine theta cos theta, and that equals the left-hand side. Far quicker than multiplying out the left-hand side terms and then applying the square identity. How you go about it is up to you. Just to illustrate that the first approach was the quickest approach, we are now going to work with the left-hand side first. So we're going to multiply out each of these terms. So we'll have sine theta minus sine squared theta cos theta plus cos theta minus sine theta cos squared theta. Okay, we're now going to apply the square identity. We're going to express sine squared in terms of cos squared, so that we can get a cos cubed term over here. And we're going to express cos squared in terms of sine squared, so we can get a sine cubed term in the last term. So that equals sine theta minus cos theta times 1 minus cos squared theta plus cos theta minus sine theta times 1 minus sine squared theta. So sine theta minus cos theta plus cos cube theta plus cos theta minus sine theta plus sine cube theta. We have sine theta minus sine theta, cos theta minus cos theta, sine cube theta plus cos cube theta, which equals the right hand side. Not particularly difficult, just takes a little bit longer to arrive at the proof. The first approach clearly is easier, but how you go about proving the identity is entirely up to you. Hence solve the equation sine theta plus cos theta times 1 minus sine theta cos theta equals 3 cos cube theta, for theta is an angle between 0 and 360 degrees. Okay, we've already proven this identity equals sine cube theta plus cos cube theta. So we're just going to apply that and equate it to 3 cos cube theta and solve. So whenever we can only solve a trigonometric equation if we're dealing with a single trigonometric ratio. We still have two trig ratios here, but we do have like terms in cos cube theta and 3 cos cube theta. So the first thing we do is just get the like terms over to the one side. So sine cube theta equals 2 cos cube theta. Now we know that tan theta is the ratio sine theta over cos theta. So if we divide both sides by cos cube theta, you'll get tan cube theta on the left, and on the right we'll just have 2. Tan cube theta equals 2, so that implies that tan theta is the cube root of 2, and we can now find the reference angle. So theta equals to one decimal place 51.6 degrees. Now the solution to this equation lies between 0 and 360 degrees. The ratio for tan theta is positive, which means the solution lies in the first quadrant or the third quadrant where the ratio tan is positive. So theta equals 51.6 is the first solution, since it is the acute angle in the first quadrant, and the second solution will be 180 degrees plus 51.6, so theta will be 231.6 degrees. So these are the two solutions to the trig equation. Question 5. The diagram shows a kite OABC in which AC is the line of symmetry. The coordinates of A and C are 0, 4, and 8, 0 respectively, and O is the origin. We are required to find the equations of AC and OB. Okay, to determine the equation of a straight line, which is given by y equals mx plus c, we need to know the gradient and one point that lies on the line. So to find the equation of AC, we've got the coordinates of the 2 points A and C, so we can find the gradient. M equals x2 minus, rather m equals y2 minus y1 over x2 minus x1. Once you've got the gradient, we can then use either of the points A or C to then determine the equation of AC. So the gradient of AC will be 0 minus 4 over 8 minus 0, minus 4 over 8 is minus a half. So we've got the gradient of AC minus a half, and we can use either of the points. The fact that A is the y-intercept, we know that C equals 4, so we don't have to substitute the point because we've got the y-intercept. So y equals mx plus c, y equals minus a half x plus 4. This is now the equation of AC. And the equation of OB, so we're just going to draw OBN. O is clearly the only point that we know on that line OB, so we are going to use the point 0, 0. What we need to do now is find the gradient of OB. Now the fact that we were told we have a kite, recall the properties of a kite is that the diagonals cut at 90 degrees. So AC is perpendicular to OB, and we know the gradient of AC. The gradient of AC equals minus a half, which means that the gradient of OB must be 2, because the gradients of two perpendicular lines, the product of the gradients of two perpendicular lines is minus 1. So we have the gradient of OB, which is 2, and we've got the point that OB passes through, the origin 0, 0. So y equals mx plus c. C is obviously 0. The gradient is 2, so y equals 2x is the equation of OB. Okay, we're now required to find the coordinates of B. Now, given that we are dealing with a kite here, another property of a kite that we need to remember is that the longer diagonal bisects the shorter diagonal. In other words, if we just call the point of intersection of the two diagonals M, that means that the longer diagonal cuts in half the smaller diagonal. So OM equals MB. In other words, M is the midpoint of OB. So to find the coordinate of B, we will first need to find the coordinates of M, and then we can apply the midpoint formula. To find the coordinates of M, M is the point of intersection of the two lines we've just found, the defining equations for AC and OB. So to find the coordinates of M, we're going to equate these two lines to each other. So 2x equals minus a half x plus 4. Multiply through by 2. 4x equals minus x plus 8. 5x equals 8. X equals 8 over 5. This represents the x-coordinate of the point of intersection, M. So to find m's y-coordinate, we substitute x equals 8 over 5 into either of these two lines. But it's far easier to substitute into the simpler one, y equals 2x. So y equals 2 times 8 over 5. Y equals 16 over 5. M is therefore the point 8 over 5, 16 over 5. So now we're going to find an expression for the midpoint of OB and equate that to the midpoint M. So the midpoint of OB will be x plus 0 over 2, y plus 0 over 2, which is just the point x over 2, y over 2. Now this point represents the point M. So in other words, x over 2 equals 8 over 5. X will be 16 over 5, and y over 2 equals 16 over 5. Y equals 32 over 5. B is therefore the point 16 over 5, 32 over 5. Question 6. The diagram shows a circle with center O and radius r centimeters. The points A and B line the circle, and AT is a tangent to the circle. Angle AOB is theta radians, and OBT is a straight line. We're required to express the area of the shaded region in terms of r and theta. Okay, the first thing we should do is mark angle OAT as 90 degrees. The reason is AT is a tangent, OA is a radius, and we know that a radius is perpendicular to a tangent at the point of contact. Why that's important is because we now have a right angle triangle in OAT. So to find the area of the shaded region, we're going to first find the area of triangle OAT and then subtract the area of the sector to get the area of the shaded region ABT. So the area of a triangle, of a right angle triangle, is a half base times height. So the base and the height are the radius and the length of the tangent respectively. It makes no difference which one is the base, which one is the height. The fact is the base and the height are perpendicular to each other, so the two sides we require are the radius and the length of tangent AT. We have the radius, which is r. Everything is going to be in terms of r and theta. So we just need to find the length of the tangent AT. So the area of the triangle will be a half times the base, r, times AT, height. Now we need to find an expression for the length of AT. We have a right angle triangle OAT. Let's just call ATX. In terms of another side of the right angle triangle, which is OA, which is the radius r, and theta, relative to theta, x is the opposite side, and OA is the adjacent side. So x over r, opposite over adjacent, will be tan theta. So x will be r tan theta. So the area of the triangle will be a half times r tan theta, which is a half r squared tan theta. That's the area of the right angle triangle. The area of the sector OAB is a half r squared theta. So therefore the area of the shaded region is the area of the triangle minus the area of the sector, which is a half r squared tan theta minus a half r squared theta, which you can clean up and write as a half r squared times tan theta minus theta. In the case where r equals 3 and theta equals 1.2 radians, find the perimeter of the shaded region. Okay, so the perimeter of the shaded region will be arc AB plus the length of AT plus BT. So we'll just call BTY for now. We know that AT is R tan theta, and we need to find arc AB. So arc AB will just indicate with an S, will be R times theta. That's the length of AB, arc AB. So that'll be R theta plus AT is R tan theta plus BT. Now, BT is part of line segment OT. So we are going to use Pythagoras' theorem here. OB is the radius of the circle. So OT squared equals OA squared plus AT squared. OT is R plus Y equals OA squared, which is R squared plus AT squared is R squared tan squared theta. Now, we were given the values of R and theta, so we have 3 plus Y all squared equals R squared. That would be 9 plus 9 tan squared 1.2. So 3 plus Y all squared equals 68.5. We'll square root both sides. So 3 plus Y equals 8.28, and therefore Y equals approximately 5.28. So that is BT. And you can just find the expression R theta. That will be 3 times 1.2 plus 3 tan 1.2 plus 5.28, which is approximately 16.6 centimeters. The geometric progression has a second term of 12 and a sum to infinity of 54. Find the possible values of the first term of the progression. Okay, so term 2 equals 12. Therefore, AR equals 12, and the sum to infinity equals A over 1 minus R, which equals 54. So A equals 54 times 1 minus R. Substitute A into this expression over here. So we will have 54R times 1 minus R equals 12. 54R minus 54R squared equals 12. 54R squared minus 54R plus 12 equals 0. We can divide through by 6, so we'll have 9R squared minus 9R plus 2 equals 0. 3R, 3R, 2 and 1, minus and a minus, so R equals a third, or R equals 2/3. Now, since we're dealing with a sum to infinity, which requires the ratio to be between -1 and 1, a third and 2/3 clearly lie in that interval. So both of these values of common ratio are valid. We now need to determine the first term of each of these progressions. So AR equals 12. So A times a third equals 12. That means that A equals 36 for the first sequence. So the first sequence is 36, 12, 4. And the second sequence, AR equals 12. That's going to be A times 2/3 equals 12. A will be 18. So the second sequence is going to be 18, 12, 8, etc. The nth term of a progression is P plus Qn, where P and Q are constants and Sn is the sum of the first n terms. We're required to find an expression in terms of P, Q, and N for the sum to n terms. Now, because the nth term is P plus Qn, this is clearly an arithmetic sequence, because the nth term of an arithmetic sequence equals A plus D times n minus 1. So this is clearly in that form. Now we need to find an expression here such that it resembles this first expression. So Tn will be A plus Dn minus D. If we just rearrange this, we will have A minus D plus Dn. So this is now in this form P plus Qn. So P is clearly A minus D and Q is D. So A will equal P plus D and the difference is Q. We're just writing it in this form because we are going to find an expression for the sum to n terms, which is given as n over 2 times 2a plus d times n minus 1. So that equals n over 2 times 2a. A is p plus d, so it's 2 times p plus d, plus d, which is q, times n minus 1. And since d equals q, that equals n over 2 times 2 times p plus q plus q times n minus 1. So that equals n over 2 times 2p plus 2q plus qn minus q. And then we can bring the half in, the n over 2 into the brackets. So we'll have pn plus qn plus a half n squared q minus a half qn, which equals Pn, Qn minus half Qn is a half Qn plus a half n squared Q. Given that the sum to 4 terms is 40 and the sum to 6 terms is 72, find the values of P and Q. So the sum to 4 terms will be 4P plus a half Q times 4, which is 2Q, plus a half times 4 squared Q. That's 16 divided by 2, that'll be 8Q. Sum to 4 terms is 40, so 40 equals 4P plus 10Q, and we can just simplify this a bit by dividing through by 2. So 20 equals 2P plus 5Q. There's the first equation. And then the sum to 6 terms will be 6P plus half times 6 times Q, so it's going to be 3Q plus a half times 6 squared. 36 divided by 2 is 18, so we'll have 18Q, and the sum to 6 terms is 72. So 72 equals 6P plus 21Q. And again, we can simplify this by dividing through by 3. So 24 equals 2P plus 7Q. That's equation 2. There's equation 1. We can now eliminate P by subtracting these equations. So we'll have 4 equals 2Q, and therefore Q equals 2. So 24 equals 2P plus 7 times 2, 14. So 2P equals 10, and therefore P equals 5. Functions f and g are defined by f of x equals a half x minus 2 and g of x equals 4 plus x minus a half x squared, where x is an element of all real numbers. We're required to find the point of intersection of the two graphs of f and g. So to find point of intersection, we equate two functions together. So a half x minus 2 equals 4 plus x minus a half x squared. We're going to multiply through by 2 to remove the denominator. So x minus 4 equals 8 plus 2x minus x squared. X squared minus x minus 12 equals 0. X and x, 3 and 4, plus 3 minus 4, so x equals minus 3, or x equals 4. X equals minus 3 and x equals 4 represent the x coordinates of the points of intersection. So to find the y coordinates of these points of intersection, we're going to substitute both x values into the simpler of the equations, which is f. So f of minus 3 equals a half times minus 3 minus 2. minus 3 over 2 minus 2, which equals minus 7 over 2. So the first point of intersection is minus 3 minus 7 over 2. And the second point of intersection is when x equals 4. I'll have a half times 4 minus 2. 2 minus 2 equals 0. So the second point of intersection is the point 4, 0. And just call these points A and B. Next, we are required to find the set of values of x for which f of x is greater than g of x. Now, one approach, which is a nice approach, is to sketch the two functions and do this graphically. If you prefer that method and you've got time to sketch it, then that's a nice way to go about solving this inequality. Alternatively, we can do it algebraically. We've already solved f of x equal to g of x, which yielded this equation, x squared, this quadratic, x squared minus x minus 12 equals to 0. So we equated the two functions and found a simplified resulting quadratic out of that. Now, the only difference between f of x equals to g of x and f of x is greater than g of x is we've replaced the equality sign with an inequality. So we are essentially going to be solving this inequality. X squared minus x minus 12 is greater than 0. The solution to the equation was x equals minus 3 or x equals 4. And these become the critical values for the inequality. So if we draw a sketch of this quadratic here, we'll have our critical values at minus 3 and 4. The coefficient of x squared is positive, so the function, the quadratic function, shapes up. So we're going to have something that looks like that. We're not interested in the turning point. We just want to know, we are just looking for the shape of the function so that we can find the solution to the inequality. Now, the inequality is greater than 0, so it's positive. So we're looking for positive y values. So the function points above the x-axis for x values less than minus 3, and the function points up above the x-axis for x values greater than 4. So the solution to f of x being greater than g of x is x is less than minus 3 or x is greater than 4. Now we're going to solve this inequality graphically by sketching f of x and g of x. Okay, so by sketching f of x and g of x, I can solve this inequality. The points of intersection have been indicated, A and B. Now we are looking for the values of x for which f of x, the y values of f of x are larger, greater than the y values of g of x. In other words, we're looking for the values of x where the straight line lies above the quadratic function. Now clearly, between a and b, we can see that the quadratic function lies above the straight line. We are looking for values of x where the straight line lies above the quadratic function. So between x equals minus 3 and x equals 4, g of x is greater than f of x. That's not what we're looking for. We're looking for f of x being greater than g of x. If we now take values to the right of 4, so for x greater than 4, we can clearly see that the straight line lies above the quadratic function. For every value of x greater than 4, if we take a point on the straight line larger than, where x is larger than 4, we can clearly see that the y value for that particular x value, the y value on f of x is a greater value than the y value for g of x. So the one solution is x is greater than 4, which agrees with our previous solution done algebraically. And then similarly, we can see that the straight line is not very clear over here, but you can see that the straight line lies above the quadratic function. So that's another solution, and that happens when the x values are less than minus 3. So x is less than minus 3. So the solution to f of x greater than g of x is x is less than minus 3 or x is greater than 4. Find an expression for f of g of x and deduce the range of f of g. So f of x is a half x minus 2. G of x is 4 plus x minus a half x squared. Therefore, f of g of x equals f of 4 plus x minus a half x squared, which equals a half times 4 plus x minus a half x squared minus 2, which equals 2 plus a half x minus a quarter x squared minus 2. So f of g of x equals a half x minus a quarter x squared. Now, we were told that the domain of each of the functions f and g was x is an element of all real numbers. So the range is going to depend on the turning point of, the range of f of g will depend on the turning point of that function. So if we just get the axis of symmetry here, we're going to need to know the turning point of this function. We can complete the square, but we've already got fractions over here, so it might be easier to just find the axis of symmetry and then substitute that x value into the function to get the turning point. So x equals minus b over 2a. So we'll have minus a half divided by 2 times minus a quarter. So minus a half over minus a half, which is 1. So f of g of 1 will be a half minus a quarter, which equals a quarter. So the turning point is going to be 1 a quarter, which means the function will shape downwards. The largest y value for the function is going to be the y coordinate of the turning point, a quarter, because all of the y values on every single point on the function will either be a quarter or less than a quarter, because the arms of the function point towards negative infinity. So the range will be y as an element of negative infinity to a quarter. That's an interval notation. As an inequality, y is less than or equal to a quarter, or you could say that f of g is less than or equal to a quarter. Function h is defined by h of x equals 4 plus x minus half x squared, for x is greater than or equal to k. We're required to find the smallest value of k for which h has an inverse. Now h of x is really the previous function g of x, but with the restricted domain x is greater than or equal to k. So to find the smallest value of k for which h has an inverse. Now h of x is a quadratic function, which means it's a many-to-one function. For h to have an inverse, it will have to be restricted such that it becomes a one-to-one function. So we need to look at the turning point of this quadratic function. So we'll just find the axis of symmetry, which will be minus b, that's minus 1 over 2 times a, which is minus a half. That'll be minus 1 over minus 1, which equals 1. So the axis of symmetry is x equals 1. H of 1 will therefore be 4 plus 1 minus a half. So the turning point is 1, 9 over 2. If we just draw a rough sketch of this function, and again, it doesn't need to be 100% accurate. So we've got a turning point. That's the turning point 1, 9 over 2. The function will look something like that. When we draw the inverse of this function, we'll get something like that. And the inverse of h clearly fails the vertical line test because we have many outputs for a single input. So we need to restrict the domain of h of x such that its inverse h to the minus 1 of x becomes, or such that the inverse function does exist. So we have to look at the axis of symmetry, x equals 1, and x is greater than or equal to k. So the smallest possible value for k is therefore 1. So you can also write this as k is greater than or equal to 1. The curve with the equation y equals x cubed minus 2x squared plus 5x passes through the origin. Show that the curve has no stationary points. Okay, so for stationary points, dy dx must equal 0. So dy dx equals 3x squared minus 4x plus 5. And to get the stationary points, we equate that to 0. This quadratic here does not factorize. There are no factors that will give the middle term of minus 4x, so we can use the quadratic formula. Now, before we attempt to solve this quadratic, firstly, we were asked to show that the curve has no stationary points, so that should be a big hint that this will not have a solution. Regardless, we need to show that it doesn't have a solution. So generally speaking, when you're looking to find a solution for a quadratic equation, you always want to find the discriminant first. You don't want to waste your time trying to solve a quadratic that doesn't have a solution. So delta equals b squared minus 4ac. That'll be minus 4 all squared minus 4 times 3 times 5, which is 16 minus 60, which equals minus 44, and that is clearly less than 0. So the fact that delta is less than 0 implies that we have non-real roots to the quadratic. So the fact that there are no roots to this quadratic over here implies that there are no stationary points. Now they're saying that they are going to denote this gradient dy dx by m. So in other words, m equals 3x squared minus 4x plus 5, and they want us to find the stationary value of m and determine the nature of that stationary point. So essentially what they're saying, we can look at this another way. This is a quadratic function, so if we had just called it y equals 3x squared minus 4x plus 5, this is just a quadratic function, and we know how to sketch a quadratic function. We can determine the stationary or turning point of a quadratic function. We are just now assigning this quadratic, 3x squared minus 4x plus 5, the letter m. So to find the stationary value of m, to find the stationary value of y equals 3x squared minus 4x plus 5, we would find dy dx and find the stationary point. We are just calling, in this instance, we are calling y m. So to find the stationary value of m, we are just going to find dm dx, which is the derivative of this function, 3x squared minus 4x plus 5, which is 6x minus 4. Now for stationary points, the derivative of the function equals 0, so dm dx equals 0. So 6x minus 4 equals 0, 6x equals 4, x equals 2/3. So there's a stationary value for this expression when x equals 2/3. Now to find the stationary value of m, we substitute x equals 2/3 into the expression for m. So m equals 3 times 2/3 squared minus 4 times 2/3 plus 5. That's going to be 3 times 4 over 9 minus 8 over 3 plus 5. That's 4 over 3 minus 8 over 3 plus 5, which is 11 over 3. To find the nature, we are going to find the second derivative of dm dx. So the second derivative of the function will be the derivative of 6x minus 4, which is 6. 6 is clearly greater than 0, which means we have a minimum stationary point. But we knew that already, because if we take this quadratic function, the coefficient of x squared is positive, which means that the quadratic function shapes up, right? Which means we're going to have a minimum turning point. So we knew that already before. We didn't have to find the second derivative, but that is generally how you find the nature of a stationary point. The fact that it's a quadratic function, it wasn't that necessary to find the second derivative. Be that as it may, it's an alternative way to find the nature of a stationary point. Finally, we are required to find the area of the region enclosed by the curve, the x-axis, and the line x equals 6. Now, it's strongly advisable, in fact, it's imperative that you always draw a sketch graph before attempting a question like this. So the function is y equals x cubed minus 2x squared plus 5x. Now, to find the area under a curve, we're going to be integrating. So before we do that, we also need to know what the boundaries, the limits of integration are. So we have x equal to 0, what? Because this function, the cubic function, passes through the origin. So we are bound by the curve, the x-axis, and the line x equals 6. So to find the boundaries of integration, we're going to substitute x equal to 0 into the function. So we'll have y equal to 0 when x equals 0. And when x equals 6, we will have y equals 174. So now to find the area of the shaded region, we will be integrating the function x cubed minus 2x squared plus 5x. The two curves, this is the first curve. The second curve, although not obvious, is the x-axis. I know it is a straight line, but we sometimes refer to, in integration circles, we refer to lines as curves themselves. So the first curve is the function itself, x cubed minus 2x squared plus 5x, and the second curve is the line, is the x-axis, the line y equals 0. The reason we're doing this is because the region enclosed by two curves is the difference in the y values. So the curve y equals x cubed minus 2x squared plus 5x and the curve y equals 0 are the curves bound by the lines x equals 0 and x equals 6. So to find the area of the shaded region, we will be integrating from x equals 0 to x equals 6. The top curve minus the bottom curve will be x cubed minus 2x squared plus 5x minus 0. So it's just going to be x cubed minus 2x squared plus 5x. And we're integrating with respect to x. Now we can integrate. Integrating x cubed gives us a quarter x to the 4 minus 2x to the 3 divided by 3 plus 5x squared divided by 2, and this is all evaluated between x equals 0 and x equals 6. So there'll be a quarter times 6 to the 4 minus 2/3 times 6 cubed plus 5 over 2 times 6 squared, less where x equals 0, so all of these terms will just be 0. So the area therefore equals 270 units squared.